Hey everybody, so today we're going to talk about the pH scale. We're going to do a bit of a deep dive into it and try to understand how it's used, when it was developed, its other features. The pH scale was first developed in 1909 by Danish chemist Søren Peter. I'm going to butcher this, so I'm not going to try to say it, but this gentleman right here is the guy that put together the pH scale. The accepted meaning for pH is the power of hydrogen or the potential of hydrogen. The exact meaning isn't real important other than we are measuring hydrogen in a water-based solution. What is the pH scale? The pH scale is a logarithmic scale with a time 10 step between each whole number, each integer. We'll talk a little bit more about this in just a second. And it is used to measure the free hydrogen in water, or more specifically, the amount of hydronium compared to the amount of hydroxides in water. The pH scale starts at 0 and ends at 14, but it technically doesn't have an end and it technically doesn't really have a beginning. 0 doesn't mean 0 as in nothing. 0 is just a starting point as in 0, 1, 2, 3. pH below neutral, and I'll explain to you what neutral is here in a second, but below neutral is considered an acid and above neutral is considered a base. So the pH scale is a logarithmic scale. Each interval changes times 10 of the previous interval. So what does that mean exactly? We take a look here. Every change between 7, which is neutral, and 8 changes by 1 unit. When we get to the 8s, we multiply that 1 times 10, and now every decimal changes by 10 units. When we get to the 9s, we go 10 times 10 equal 100, and now every decimal point changes by 100 units. Take a look at what that looks like here. So 7 to 7.1 changes by 1 unit. 8 to 8.1 changes by 10 units. 9 to 9.1 changes by 100 units. 10 to 10.1 changes by 1,000 units. And that keeps going on and on. That's how a logarithmic scale works, and that's how our pH scale works. So, what is meant by neutral? Water is considered neutral when the hydronium and the hydroxide ions are equal to each other at a 1-to-1 ratio. They're equal. Water is considered an acid when the hydronium is greater than the hydroxides. The smaller the number, the stronger the acid becomes. So when we're going off in this direction, as these numbers get smaller, the acid is getting stronger. Water is considered basic or a base when the hydroxide ions are greater than the hydronium ions. So as the numbers get bigger in this direction, that base is getting stronger. So this is just a quick overview of what I just said. An acid has a greater amount of hydronium than hydroxide, and that means it's a less than 7, less than neutral. Neutral is when they even out with each other, 1-to-1 ratio. Now they're even, that's considered neutral, pH 7. Basic is when the hydronium is less than the hydroxide, that meaning the pH is higher than 7, that's considered basic. The pH scale is using interval data as opposed to a true ratio. It has ratio characteristics. We now understand that like 6.9 is changing at a different pace than 5.9. In order to be a true ratio, these two numbers would have to be changing at the same pace. They don't, so it's not an actual ratio, but we can calculate a ratio within that interval. So if we take a look at this and we go, if 6.9 has one more hydronium over hydroxide, now they're not equal anymore, it has a 2-to-1 ratio. That's 6.9. If it goes and it has 2 parts of hydronium, so now it has 3 hydroniums, because we had our original 1-to-1. We've added 2 more, now we have a 3-to-1 ratio to it. And we go the other direction here too. If we end up with, we started off with neutral, our 1-to-1 ratio, and we add 1 more hydroxide to it, now we have a 2-to-1 ratio at a pH of 7.1. If we go and we add two hydroxide ions to it, we now have a 3-to-1 ratio or pH 7.2. That's how it works. Do fish have problems with changing pH? And the answer is no, fish do not have problems with changing pH. What fish have problems with are 2 things. One is a rapidly changing pH, and 2, a rapidly changing pH because we don't understand how our scale works. It's really easy to look at these decimal points and think, well, those changes are relatively small, but they're not. Part of the problem is we don't really understand our tools too well. We look at our API test kit chart, and it's really easy for us to misinterpret this stuff. We look at 8 to 8.2, and we look at 7 to 7.2, and what we need to understand, and I hope we do understand by this point in the presentation, that this change here is much more rapid than this change here. This only changed 2 intervals, and this one changed 20 intervals. One thing about these pH pens that we need to understand is, although they're more accurate, they're not necessarily more precise. The further away we get from neutral, the less precise they become. You can think of it like this. If I have a dartboard and I'm throwing darts up close and I'm hitting that middle every single time, I hit the middle, not only is that accurate, but that's very precise. Now if I start stepping back, and I'm still hitting the dartboard, but now I'm hitting outside that ring and I'm only once in a while hitting that middle. I'm still relatively accurate, but now I'm no longer as precise. If I step back even further, now I'm hitting a larger ring, and I'm still only maybe hitting that middle once in a while, but I'm not hitting it every time. So although I'm still accurate, my throwing is no longer as precise the further away I get from the dartboard. And you can think of neutral as the same thing as that middle part of that dartboard, and the further away we get from that middle, the further away we get from 7, the less precise this tool is actually going to be, because of the intervals that are involved in between each step. Just a side note here, and I thought this was pretty interesting, is that hydrogen is the most abundant element in the entire universe. And it's in every water drop that you ever drank, it's in every breath of air you ever breathe. It powers or fuels our sun and all the stars in the sky. It's pretty amazing stuff. It's literally the building blocks to everything in the universe. Now we have in aquaponics, we have what I call the sweet spot. And the sweet spot for aquaponics is somewhere between 6.8 and 7.2. Generally speaking, our fish are going to be happy in that spot and our plants are going to be happy in that spot. But that spot is a bit of a compromise, as fish tend to prefer things a little bit more basic and plants seem to prefer things a little bit more acid. So let's take a look at some plants and fish that I laid out here. So we have tilapia, and a lot of people grow tilapia because they're pretty much bulletproof. Tilapia, although it has a huge pH range, like absolutely incredible that it can handle this much pH. It can go from 3.7 to 11, anywhere in between there. But it's optimal where the fish is happiest, where it's going to eat the best, where it's going to grow the best, is somewhere between 7 and 9. So fairly basic. Trout don't have nearly the range tilapia does. Goldfish, a little bit narrower as far as where they're actually really happy. Guppies, which is one of the ones I use. I use guppies over here off to my left side, maybe your right side where you're looking. They have a fairly narrow pH range. They're happiest in a very basic solution between 7 and 8. Now we get into some plants. Lettuce, which is almost basically the tilapia of the plant world, it's happiest between 6 and 6.5 is where it'll grow best, but you can go anywhere from 5.5 to 8, and it'll do pretty good in there. Tomatoes, it can grow anywhere from 5 to 7.5, but it's happiest in acid conditions 5.5 to 6.5. That's where it's going to grow the best. Cucumbers, 6 to 6.5, and a maximum pH range of 5.8 to 8. What becomes really interesting is when we start talking about the maximum pH range of, like this plant here, of tomatoes. If we take a look at this next chart here, what we start seeing is when we hit 7.5, what ends up happening? The calcium starts to drop out and we start getting blossom end rot. And I will also tell you from personal experience that if you get your pH too high on your lettuce, you'll start noticing calcium deficiencies because the calcium is no longer available to the plant, which I thought is pretty interesting when you start looking at some of these things. If you get your pH too low, sometimes things that your plants need, such as iron here. Iron actually can become toxic to a plant if the pH is too low. And the reason it becomes toxic to that plant is because it becomes too available to that plant. And that starts hindering its ability to take other things that it needs. So if we take a look at say we're getting down into the 5.5 area where your iron has become very, very available, take a look here at what's start to become less available. Things like nitrogen, phosphorus, potassium. Those things are what your plants absolutely need the most of. So it's pretty interesting stuff, and how pH can affect the different uptakes and stuff for your plants also. If you'd like me to do a deeper dive into how this chart here works, make a comment down below. If you got something out of this video, if you feel like maybe you can understand your pH scale a little bit better and understand how it works, if you got that out of the video, I would appreciate a comment. Please subscribe to the channel. It certainly is going to help make videos like this possible. Like, share, and subscribe, and have a fantastic day.